Hello everyone, this is Veni Maditati. In this video, I am going to explain units and dimensions, and I am sure that after watching this class, you can solve every question regarding this topic. So the topics to be covered here are measurements, dimensions, error calculations, and significant figures. Firstly, we have to know what is meant by physical quantity. Anything that can be measured is called as physical quantity. For example, if we take sugar, we can measure it like 1 kg of sugar, 2 kg of sugar, in such way. Anything which we can measure, that can be called as physical quantity. And then coming to types of physical quantities, there are two types of physical quantities. These are fundamental and then derived quantities. The example for fundamental quantity are length, mass, time, temperature, amount of substance, electric current, luminous intensity. And the derived quantities are extracted from the fundamental quantities. An example for this derived quantities are area, which is extracted from length, that is L square, volume, L cube. It was also derived from the fundamental quantities. Those are called as derived quantities. And then density, which is equal to mass by volume. After measurement, result is expressed in terms of unit. For example, if we take, I have finished a certain work in 2 seconds. If you simply say, I have finished this work in 2, what does 2 refers to? Either seconds or minutes or hours. It is meaningless. So after measurement, we should represent a result in terms of the number as well as unit. Here 2 seconds, 2, which is a number, and second, which is a unit. So a physical quantity should be represented in the terms of number and unit, that is NU. Here N represents the number and U represents the unit. For example, length, that equal to 10 centimeter, time 2 seconds, like that. And now coming to fundamental units, there are 7 fundamental units. These are mass, length, time, temperature, amount of substance, electric current, and then luminous intensity. SI unit for mass is kilogram. For length it is mass. For time it is second. For temperature Kelvin. For amount of substance mole. For electric current it is ampere. And for luminous intensity it is candela. And the symbol for mass is kg. For length it is meter. For time it is second. For temperature it is Kelvin. For amount of substance it is mole. For electric current A. For luminous intensity CD. And now coming to supplementary units. Here we have plane angle and solid angle, and the name of the unit for plane angle is radian and its symbol is theta. For solid angle it is steradian and its symbol. So usually plane angle is taken for 2-dimensional objects and solid angle for 3-dimensional, like sphere and a frustum cone. For a frustum cone, the angle made here, by joining all this, here an angle is formed. That angle is called as solid angle. And now pi radian is equal to 180 degree. You have to remember this. And one more important point regarding supplementary unit is these have units but they do not have dimensions. This plane angle and solid angle, they only have unit but they does not have any dimension. And some other units of length, there were only few questions asked regarding this topic. It's just enough to remember these values. Now coming to astronomical unit. One astronomical unit is equal to 150 into 10 power 6 kilometer. And light year. What is meant by light year? The distance traveled by light in 1 year. As we know that distance that equal to velocity into time. By calculating this, you just remember this value. 1 light year is equal to 6324 1 astronomical unit. And coming to parsec, you just simply remember this value. 1 parsec is equal to 3.26 light year. And regarding this, few questions were asked previously. You have to remember this order. 1 astronomical unit is less than 1 light year, which is less than 1 parsec. You just remember as alpha. This is just a trick to remember. And now coming to dimensions. So what is meant by dimensions and how do we write dimensional formula? I'll explain you this. A derived quantity which is written in the combination of fundamental quantities raised to their powers. Any dimensional formula is represented standardly as MLT raised to their respective powers. Let us say m power x, l power y, and t power z. I'll give you some examples regarding this. Now coming to area. We know that area that is equal to length into length, which is equal to L square. So this can be represented as, here it is independent of mass and temperature. So it can be expressed as m power 0, L square, and t power 0. We can simply write in shortcut as L square. And now coming to volume, which is equal to length into breadth into height. So this breadth and height, which were also similar to length. So we write this dimensional formula as it is also independent upon the mass and temperature, m power 0, L cube into t power 0. Simply we can write it as L cube. And now coming to density, we can write density as mass by volume. So it is dependent on mass. So m power 1 by volume. What is the dimensional formula for volume? It is L cube. So if it comes here, then it becomes L power minus 3. Now the dimensional formula for density is m power 1 and then L power minus 3. Similarly, for acceleration, we know that acceleration that equal to velocity by time. So what is the dimensional formula for velocity? Lt power minus 1. As we know that velocity is equal to displacement by time. Here for displacement it is L, and for the time it is t power minus 1. Okay. So the dimensional formula for acceleration becomes Lt power minus 1 by time t. So Lt power minus 2. And now coming to force. We know that force is equal to mass into acceleration. For mass, we write m, and for acceleration it is Lt power minus 2. So the dimensional formula for force will become m power 1 L t power minus 2. And now coming to work. We know that work done is equal to force into displacement. What's the dimensional formula for force? M L t power minus 2, and for displacement it is L. So m L power 1 L power 1, that is equal to L power 2. So m L square t power minus 2. Now for energy or work, for both we have the same dimensional formula. How can we derive dimensional formula for this energy? Either it may be kinetic energy, potential energy, or some other. You'll get the same dimensional formula. Let us take kinetic energy. So we know that kinetic energy is equal to half mv square. Now we know that as here it is dependent on mass, m power 1 into, for velocity we know that it is Lt power minus 1, and by making whole square, Lt power minus 1 whole square. So L square t power minus 2. Now the dimensional formula for energy is m L square t power minus 2. Here you have to be aware of a term known as gradient. What is meant by gradient? A certain physical quantity per unit length is called as gradient. You simply remember that if they ask gradient, you have to put the dx in denominator. For example, velocity gradient, that is equal to dv by dx, velocity per unit length. Simply we write it as delta v by delta x. And coming to this principle of homogeneity, it is very important, and more questions were asked from this topic. The quantities which are separated by equality or addition or subtraction should have same dimensions. I'll explain you. Here, if we take any physical quantity, those were separated either by the equality or addition or subtraction. These should have the same dimensions. For example, if we take v is equal to u plus at, here this equation is separated by an equality and an addition. So the dimension of v should be equal to dimension of u should be equal to the dimension of at. We know that this is according to the laws of motion. Final velocity v is equal to initial velocity plus acceleration into time. Now the dimension of final velocity and the dimension of initial velocity, that both remain same, that is Lt power minus 1. And now coming to at, here acceleration into time, that also gives LT power minus 1, as LHS is equal to RHS. And we have an important equation. This was repeated in JE many times. This was from ideal gas in gaseous state in chemistry. P plus A by V square into V minus B, that equal to nRT. Here P represents pressure, V for volume, N for number of moles, R for gas constant, and T for temperature, where A and B are constants. Here is a question: find the dimensions of A and B. Anytime you remember that if there was some equation separated by this equality, addition or subtraction, then you have to apply principle of homogeneity there. Now, as these were separated by this equality, addition and subtraction, you just use principle of homogeneity here. Now, by applying the principle of homogeneity for this P plus A by V square, the dimension of P should be equal to the dimension of A by V square. So the dimension of A is equal to dimension of P into dimension of A square. So what is dimensional formula for pressure? We know that the pressure is equal to force by area. As we know that the dimension formula for force is mL T power minus 2. For area it is L square. So m L power minus 1 T power minus 2. This is the dimensional formula for pressure. And for volume it is L cube whole square. In that way you get the dimensional formula for A. And we also want to find dimensional formula for B. So the dimension of V should be equal to the dimension of B. Here as V is the volume, so its dimensional formula is L cube. So the dimensional formula for B is also equal to L cube. And now coming to uses of dimensional formula. There were three major uses of this dimensional formula. First one is it is used to find the correctness of given equation, and secondly to establish relation among various system of units, and thirdly it is used to establish relation among various physical quantities. Let us go through the first one, that is to find the correctness of a given equation. For example, we know that S is equal to ut plus half at square. This was from laws of motion. If we place S is equal to 2 by 3 ut plus 7 by 2 at square, and by applying the principle of homogeneity, we know that the dimension of S should be equal to dimension of ut should be equal to dimension of at square. This is because this constant does not have any dimension. So as these were separated by the equality and as well as plus, we should apply principle of homogeneity here, and the dimension of S should be equal to dimension of ut, which is equal to the dimension of at square. Now as the dimension of S is equal to dimension of ut, we get dimension of S, that is length, so L power 1, and the dimensional formula for ut, here u is the initial velocity. For velocity it is LT power minus 1, and for time it is T power 1, so it becomes L. Here LHS is equal to RHS. And now S should be dimension of S should be equal to the dimension of at square. See, according to the principle of homogeneity, dimension of S should be equal to dimension of ut should be equal to the dimension of at square. So here the dimension of S is again that is distance L power 1, and for at square, for acceleration it is LT power minus 2, and for time it is T square. So its dimension becomes L. Again LHS is equal to RHS. But this was not correct according to the laws of motion, because according to laws of motion the formula is S is equal to ut plus half at square. Okay. And now to establish relation among various system of units. By using this dimensional formula, we can establish the relation among various system of units. For example, N1, U1, for example, we take 10 centimeter, which is equal to 0.1 meter. Here, N1, U1 is equal to N2, U2. What is N1? It is number. U1, unit. N2, number into unit. Here, 10 centimeter. For example, let us say this pen is 10 centimeter. If you say that this pen is equal to 0.1 meter, then does it length changes? No, it remains same. So either 10 centimeter or 0.1 centimeter, it is same. To establish the relation among that various system of units, we'll use this dimensional formula. Let us have an example to understand clearly. Now, here the question is, the density of a material in SI unit is 128 kg per meter cube. In certain units in which the unit of length is 25 centimeter and the unit of mass is 50 gram. So we have to find the numerical value of density of the material. We know that density that is equal to mass by volume, that is m by L cube. As we know that N1 U1 is equal to N2 U2. If they give a certain quantity and they ask to express in the another unit, then you have to use this N1 U1 is equal to N2 U2. Now they have given 128 kg per meter cube, that is equal to, so N1 128 U1 kg per meter cube, that is, we have to find N2 here, and it was given as 25 centimeter and 50 gram. So as here they have given gram per centimeter cube, you have to convert it either into kg per meter cube or else convert these into gram per centimeter cube. Both are same. So N2 into 50 grams. So 50 into 10 power minus 3 kg by 25 centimeters. So 25 into 10 power minus 2 meter cube. And now by simplifying this, we get N2 is equal to 40. If they ask you to establish the relation among various system of units, that is from gram, kilogram, centimeter, meter, in such questions you use N1 U1 is equal to N2 U2. And now thirdly, it is used to establish relation among various physical quantities. For example, length and acceleration due to gravity are considered as fundamental quantities. So now you have to express time period in terms of this length and acceleration due to gravity. So you write the dimension of t. It is directly proportional to length and acceleration due to gravity raised to some power. We don't know that. So t is directly proportional to L power x into z power y. Now if you remove this proportionality, then you will get a proportionality constant. However, there is no dimensional formula for the constant value. So t power 1, that is equal to, here for length it is L power 1 raised to x. And for acceleration due to gravity, it also have the same unit as that of acceleration, which is equal to LT power minus 2 raised to the power 5. So t power 1, that is equal to, here L power x into L power y, that is equal to L power x plus y into t power minus 2y. And now by comparing the exponents from LHS and RHS, you get those values. So here, however, it is independent of L. So x plus y is equal to 0 and x is equal to minus y, and minus 2y is equal to 1. From this we get y is equal to minus 1 by 2. So now t is directly proportional to L power x 1 by 2 into z power minus 1 by 2, which can be written as t is directly proportional to L power 1 by 2 by z power 1 by 2. That is t directly proportional to L by z. And let us have a look at another question. If modulus of elasticity and density are considered as fundamental quantities, then how velocity is related to them? So here velocity is directly proportional to the modulus of elasticity as well as density. See, for this to calculate dimension, if you once go through revision, then you will get aware of all the formulas. If you know that formula, you can easily calculate those dimensional formulas. Okay. As we know that modulus of elasticity is equal to stress by strain. By using this, we can calculate the dimensional formula for elasticity. As we know that the dimensional formula for velocity is LT power minus 1, and now for modulus of elasticity it is m L power minus 1 t power minus 2 raised to the power x, and for density it is ml power minus 3. As we know that density is equal to mass by volume, its dimensional formula becomes ml power minus 3 raised to the power y. Now again, by comparing this coefficients of both LHS and RHS, you will get the values of those x and y. In such way you solve this question. And let us have a look at another question. If momentum, area and time t are taken as the fundamental quantities, then the dimensional formula for coefficient of viscosity is, see, this coefficient of viscosity is repeated many times, so you just by heart the dimensional formula for the coefficient of viscosity. You can derive it when once you go through fluids, then you will get formula related to this, that is force is equal to 6 pi eta AV. From that we can calculate the coefficient of viscosity. So as here they have given that the coefficient of viscosity is expressed in terms of momentum, area and as well as time. So you take momentum raised to the power x, area power y and t power z. We get the dimensional formula of the coefficient of viscosity as ml power minus 1 and t power minus 1. For momentum, we know that mass into velocity. So by that you will get the dimensional formula as mlt power minus 1 raised to the power x. And for area, it is L square raised to the power y and time t power 1 power z. And again, by comparing these coefficients, you will get the value of x, y, z. Okay. And another last question regarding this. If velocity, time and force are chosen as base quantities, what will be the dimension of mass? So the dimension of mass will be, here this dimension of mass is dependent upon this velocity, time as well as force. So v power x, t power y. So this dimensional formula for mass can be represented in the terms of velocity raised to the power x, time to the power y and force to the power z. So as we know, the dimensional formula for velocity is Lt power minus 1, for time it is t power 1 and for force it is mlt power minus 2. And again by comparison we'll get the values of x, y, z. And now here I am going to give you a few problem solving techniques. If you get sign of something like a sign of box, like sign of x square, like that, cos of something, tan of something, these were the dimensionless quantities. And anything which is inside this box, we simply write as m power 0, l power 0 and t power 0, as it is dimensionless. And if you have 2 power something, that is constant power something, e power something, log of something to the base e, those were also dimensionless. And that something which is present, the dimension, it is also dimensionless, so we can write it as m power 0, l power 0 and t power 0. Here is some example regarding to it. Y is equal to alpha log beta t to the base e. Now here we have to find the dimension of beta. We know that log of something to the base e is dimensionless. That is, this beta t is dimensionless, so it should have dimension as m power 0, l power 0, t power 0, as however it is dimensionless. Now beta is equal to m power 0, l power 0, t power 0 by, here t is time, so by t. So we get the dimensional formula for beta as t power minus 1. Now we are going to enter into error calculations. We have finished units and dimensions, and now we are going through error calculation. For example, if by measuring the cap for this pen, one guy measured it as 3.2651 centimeter and another X person have measured it as 3.2652 centimeter. There was error. See, any measuring instrument contains some error, or else there may be error because of the way we see it, or by the measuring instrument. Okay, so we have to calculate that error. A is equal to A plus or minus delta A. See here, to calculate that error, here these two quantities have same up to 3.265. These were varying only after this. Here it came 1 and here it came as 2. So 3.625 is common, plus or minus the error in these both is 0.0001. So in such way we'll calculate error. I'll give you more example, you will get clarity. These errors were further classified into 3 types. Those were absolute error, which is also called as true value, and then relative error, and then percentage error. Now coming to the absolute error. It is like mean, that is sum of observations by total number of observations. So A1 plus A2 plus A3 plus and so on, these were the observations, and there were total n number of observations. Now coming to relative error. Those relative error is the change by original, that is delta A by A. And for percentage error, you have to make relative error into 100, that is delta A by A into 100. Now combination or propagation of errors. This is very important, and most of the questions regarding error were asked. Now Z is equal to A plus B. Z plus R minus delta Z is equal to A plus R minus delta A plus B plus R minus delta B. Now the maximum possible error can be, that is Z plus R minus delta Z, that is equal to A plus B plus R minus delta A plus delta B. This is in case of addition. You simply add this to A plus B. You simply add these exact values and then these delta A and delta B. While making questions, you will get clarity regarding this. And in case of subtraction, that is, if you have Z plus R minus delta Z, that is equal to A plus R minus delta A minus B plus R minus delta B, you simply subtract these both, A minus B plus R minus delta A plus delta B. Now, in case of multiplication and division, it is easy. If you have something Z is equal to X into Y, then you can write it as delta Z by Z, that equal to, here multiplication, it becomes as addition, just to remember. So delta X by X plus delta Y by Y. Now, in case of division, if you have Z is equal to X by Y, you can write this as X into Y power minus 1. You remember that if there was negative also, if there was something in the exponent, it comes into the multiplication. It comes as a product, and you don't take negative sign. You should not consider the negative sign here. So as Z is equal to X by Y, which can also be written as X into Y power minus 1. Now delta Z by Z is equal to delta X by X. Now as it is minus 1, you should consider only its magnitude. You should not consider the negative sign. So plus delta Y by Y. That is, in case of exponents, if you have X rise to some power, Y rise to some power, and like by C, under root of C into D. Now in that case, you write as delta Z by Z, that equal to, here X cube. So this power comes into multiplication, 3 into delta X by X. And now here this multiplication becomes as addition, that is plus. Here as it is power 2 into delta Y by Y plus, as it becomes C power minus 1 by 2, you only consider this positive value. So plus 1 by 2 into delta C by C plus delta D by D. Hope you are clear. Now, let us go through a question for more clarity. The initial and final temperature of a water bath are 18 plus or minus 0.3 degrees Celsius and 40 plus or minus 0.5 degrees Celsius. Now, what is the change in temperature of the bath? This change in temperature, let us say as theta. So delta theta, that equal to final minus initial, that is equal to theta 2 minus theta 1. So 40 when you have to subtract, you make like this. So 40 minus 18 plus or minus delta A plus delta B. So plus or minus 0.3 plus 0.5. So you get 22 plus or minus 0.8 degrees Celsius. You just simply by head this formats. If you make few questions, you'll automatically remember it. And coming to another question, for z is equal to a square x cube y power 1 by 2, where a is a constant. If percentage error in measurement of x and y are 4%, 12% respectively, then the percentage error for z will be here. You remember one thing, for constant we cannot calculate this error. Okay, as here they have given z is equal to a square x cube y power 1 by 2, and however a is a constant, you should not take it. Now delta z by z, as they were asking percentage error, so you should make delta a by a into 100. So in such way, delta z by z into 100. Now as these were in product, rise to some exponent, so this exponent should come into multiplication. As here a square is constant, you just remove it. For x cube, as here 3 is the exponent, so 3 into delta x by x into 100 plus 1 by 2 into delta y by y into 100. You know that here they have mentioned that percentage error in measurement of x, that is delta x by x into 100, was already given as 4. So you simply replace it by 4. And for delta y by y, it was mentioned as 12. And by simplifying it, you will get the value as 18. And the length and breadth of a rectangle are 4 centimeter plus or minus 0.2 centimeter and 9 centimeter plus or minus 0.3 centimeter respectively. Now you have to find the percentage error in calculation of its area. As they have mentioned, for length it is 4 plus or minus 0.2. For breadth it is 9 plus or minus 0.3. To calculate area, we know that area is equal to length into breadth. So as we have to calculate the percentage error, we have to make delta a by a into 100. So delta a by a into 100 is equal to delta l by l into 100. As it was in product, we have to make it as addition. So plus delta b by b into 100. You simply replace those values and simplify, you'll get the answer. And now coming to this rounding off, which is very much useful in advanced. You'll also often get in numerical values in mathematics and as well as physics. There were 3 simple rules. If you just remember this, then you can solve every question regarding this. Coming to rule number 1, if the last significant digit is less than 5, then you should drop it. I'll go through few examples, then you will get clarity. If the last significant digit is less than 5, then drop it. For example, 3.0251. Here the last significant digit, which is less than 5. So you just simply drop it. I mean, you don't consider it. So 3.205. And coming to rule number 2, if the last significant digit is greater than 5, then increase the preceding digit by 1 and drop that digit. So for example, if you take 3.02057, here the last digit is greater than 5. So you have to increase those preceding digit by 1 and drop that last digit. So it becomes 3.206. And if you take 3. And now coming to rule number 3. If the last digit is equal to 5, that is, if last significant digit is equal to 5, then look at the preceding digit. If the preceding digit is even, then drop those last significant digit. If the preceding digit is odd, then increase the preceding digit by 1 and then drop that last significant digit. For example, if it is 3.2065, here the last significant digit is equal to 5 and the preceding digit is even, as is case 1. So you have to drop this last significant digit. So you get 3.206. And if it was 3.2075, That is, the last significant digit is 5 again, and the preceding digit is odd. That was according to this 2. Then you have to increase this preceding digit by 1, and you have to drop the last significant digit. So you get 3.208. And now coming to significant figures, one of the most important subtopic in this units and dimension. So there were simple rules to remember. If you remember these 4 rules, then you are done in this topic. So coming to rule number 1, every non-zero digit in a reported measurement is assumed to be significant. That is, for example, if you take 543, 627, like this 582973. So as every non-zero digit in a reported measurement is assumed to be significant. Here, these all were the non-zero digits, so you have to consider these as significant. Here the number of significant digits are equal to 1, 2, 3. For this 627, 1, 2, 3 again. For here you have 6 digits, so it is 6. And now coming to rule number 2, zeros appearing between non-zero digits are significant if there were zeros present between non-zero digits, then those were also considered as significant. For example, if you take 5006, here these zeros were in between of this non-significant. These zeros are in between the significant digits. That is, in between the non-zero digits. Sorry, these zeros are placed in between non-zero digits, so these were significant. It means you have to consider these digits also. So here the number of significant digits are 4, and here also the number of significant digits 1, 2, 3, 4, 5, as these were placed in between the non-zero digits. And for here, as these zeros were placed in between non-zero digits, and this zero is also placed between the non-zero digit, you get 1, 2, 3, 4, 5, 6, 7. So 7 significant figures. And now coming to the rule number 3, leftmost zeros appearing in front of a non-zero digits are non-significant. I repeat it once again. Leftmost zeros appearing in front of a non-zero digits are non-significant. Example for this rule 3. Here 0.1, leftmost zero appearing in front of a non-zero digit. Those were non-significant. It means you should not consider those. If you have 0.1, then the number of significant digit is only 1. If you have 0.001, then also it is only 1 significant digit. If you have 0.00507, so this leftmost, these were non-significant. As this 0 is placed in between the non-zero digits, these were significant. So the number of significant figures are equal to 3. And coming to rule number 4, zeros at the end of a number will be counted as significant if and only if they are at the right side of a decimal point. That is, if you take 506 560700, here you should not consider these two zeros, as this rule says that zeros at the end of a number will be counted as significant if and only if at the right side, they are at the right side of a decimal point. If you come here 506700.0, as this 0 at the end of the number are at the right side of this decimal point, we consider it as a significant digit. So in this case, the number of significant digits are 7. And of coming to this example 560700.1, so here you get 7. And now coming to addition, subtraction, multiplication and division regarding this significant figure. Now let us go through the addition and subtraction using this significant figures. Here you just remember simply 2 steps. That is, step 1 is do normal addition or subtraction however you do. For example, if you have 2 numbers, that is 33.432 and 1.82, you just make general addition, so you get 35.252. And next, second step is to identify among the given number which has the least digits after the decimal point. So after the decimal point, here you can see that 1 2 3 4 5 digits are there in total here. After the decimal point, here there were 3 digits, five in total. After decimal point, only 3. After decimal point, only 2. Among 3 and 2, which is the least? 2 is the least. So for the final result, there should be only 2 significant digits after the decimal point. So the final answer, that is by rounding off, we get as 35.25, as we have to consider the least significant digit. But it was completely reverse in case of multiplication and division. So if you multiply 33.4 with the 21.781, then you will get some answer. That answer should be rounded off to 3. This is why, because among these given these two, here for multiplication and division you have to count total number of significant figures. Here the total number of significant figures are 3, and here the total number of significant figures are 5. So the answer should be rounded off to the least number of total significant figures. Here the least number is 3, here it is 5. So you have to consider only 3 significant figures. After multiplying this, you have to make only up to 3 significant figures. This is all about your units and dimensions. And if you have any doubts regarding this topic, you can comment me. And if you want a session notes, if you comment me, then I'll provide you notes. And if you want separate video regarding these questions, if you comment me that you want questions, I'll make a separate video for questions regarding this topic. If you have any doubts, please ask me in comments. Thank you for watching, and subscribe my channel for more videos. And screw gauge and vernier calipers are also related to this, included in this units and dimensions. But I'll make a separate video for this screw gauge and units and screw gauge and this vernier calipers. Thank you for watching my video, and subscribe my channel for more videos.